everyone, for today's lesson we are going to learn how to graph functions involving the natural base e. Before we get started with talking about what the natural base actually is, I would like you to please go ahead and complete this warm-up by pausing the video and factoring each of these expressions. The first expression is 2x to the third power minus 16y to the third power, and the second expression is x to the fourth power minus 16. When you have an answer, please go ahead and restart the video and we'll see how well you did. All right, for problem number 1, hopefully you noticed that 2x to the third power and 16y to the third power both have in common a 2. So whenever you see problems that have two terms in it, you want to look for one of two things. You either want to look for a greatest common factor, or one of three things, should I say, a greatest common factor, or a special case like dots, or a sum or difference of cubes. You want to look for something that's special. And so in this case, I'm going to factor out a 2, because both of these two terms have in common a 2. And my leftovers is going to be an x cubed minus 8y cubed. And what x cubed minus 8y cubed actually is a difference of cubes, which means that we have ourselves a SOPS situation. So I'm going to write 2 times a binomial times a trinomial. And in my binomial, I'm going to take the cube root of the first term minus the cube root of the second term. So I have x minus 2y. Then I'm going to do square opposite product square using my binomial. So I'm going to have x squared, opposite of a minus is plus, product 2y times x is 2xy, and then squared. 2 squared is 4, so we have plus 4y squared. So hopefully you saw that this would be a SOP situation and you were able to factor it completely. Always keep your eyes peeled for opportunities to break expressions down even further. For number 2, this is a dots written in quadratic form. So we're going to break this problem down into an x squared plus 4 and an x squared minus 4. If you made it this far, that's pretty good, but you didn't make it all the way because x squared minus 4 is also a dots. So we're going to break just that down. The x squared plus 4 is what we call prime. So if you ever see a sum of squares, like in this case, x squared plus 4, we call that an SOS, and an SOS means you just simply cannot do it. So I have an x squared plus 4 times an x plus 2 and an x minus 2. And there's your full factorization. Always keep your eyes peeled for opportunities to break down expressions even further. And that's essentially the moral of the story for our warm-up for today. So now let's go ahead and talk about our lesson. So our learning targets for today is to be able to say, I can simplify expressions using the natural base e, both with and without a calculator. So there's going to be problems where you'll have to work with a calculator and other problems where you won't have to work with a calculator. You won't have a calculator to work with. And then I can graph natural base functions using a parent function, reflection, stretch, shrink, translation table. So we're going to be graphing these functions with our natural base that we call e. Then I can use the natural base to solve real-world problems. And I can find the ending balances of accounts when given an interest rate for interest compounded continuously. So continuously is a new concept. We've learned how to compound interest annually, monthly, semi-annually, and daily. But now we're going to talk about how to compound interest continuously. So now let's go ahead and talk about what e is. The natural base e, that number is an irrational number. So e is like pi. It represents a number that continues forever and ever without any sort of pattern. So it's an irrational number. It's defined by the following. As n approaches positive infinity, 1 plus 1 over n to the nth power approaches 2.7182128. Do you have to memorize all of those numbers? Continuing on forever and ever? No. I'm only interested in you knowing that this is 2.718. So whenever you see the letter E, we're going to call it 2.718. The language of as n approaches positive infinity, 1 plus 1 over n to the nth power, is something that we're going to explore more when you get to calculus. Currently, we are not in calculus, so therefore we are not going to talk about that language at this time. I think that's maybe even introduced in pre-calculus at the end of pre-calculus, but we're not there yet, so we're not going to focus on this part. The most important part that I need you to know is that E is equal to 2.718. So I need you to know and memorize this number. Now the letter E, or the number E, is a button that's on your calculator. So I'm going to bring up both calculators and I'm going to show you where it's located on both calculators. So wherever you see ln, that means the natural log. There's going to be an E value. So you'll notice that it says e to the x. That's where E is located. So you would press second ln and then that would produce an E. On a regular calculator, like a scientific calculator, what you're going to see once again is an ln button, and then you'll see this little e to the x power, and you'll have to get there by pressing the second ln button. If your calculator does not have an E button, then I would recommend strongly that you start working with a calculator that does. So if your scientific calculator doesn't have that button, either obtain one from somebody that you know, purchase one, or use one from my classroom, but just know that I have a limited supply. So now here we go. We're going to simplify expressions containing E. Just like we would with other letters that we know of, we kind of pretend as if it's a variable until we can't pretend anymore. So if you see e to the 6th times e to the 3rd, we think about our exponents rules, where we're multiplying two powers with the same base, so therefore we add our exponents. So this is simply e to the 9th. 3 plus 6 is 9. Next, for letter B, we have 18e to the 6th divided by 2e to the 4th. I'm going to divide 18 divided by 2, that's equal to 9. And I'm going to subtract my exponents because they have the same base. 6 minus 4 is 2. So because there are more e's on top, that's where the e squared will be. So our answer is going to be 9e squared. For letter C, whenever we have 4e to the 3x power squared. So that means because the main operation is multiplication, each piece is going to be raised to the second power. So this is 4 squared times e to the 6x power, and 4 squared is 16. So this is 16e to the 6x power, and we're just going to leave our answer just like that. For letter D, we're multiplying all of these powers with the same base, so we're going to add the exponents. So this is e to the negative 3 plus x plus 5x power. So I'm simply adding my exponents together. I'm going to combine my like terms, and my answer is going to be e to the 6x minus 3 power. And finally, for letter E, we have 4e to the 3rd power squared divided by 8e to the 5th power. So I'm going to take care of my exponent first by making this 4 squared times e to the 6th divided by 8e to the 5th. 4 squared is 16, so this is 16e to the 6th divided by 8e to the 5th. 16 divided by 8 is 2, so this is 2e to the 1st power, because 6 minus 5 is 1. So we're simply going to write this as 2e. Unless they ask you to evaluate, I want you to leave your answers in terms of E. So if you're asked to simplify the expression, just leave your answer in terms of E. So please note, in an expression, E comes before a variable. And that is because it is considered a number and not a variable. So there might be some problems where you will have an EX. And if you have that, the E has to come before the X. You can also look at it as if it's in alphabetical order, if that helps you. But we always put E before a variable. So now what we're going to do is we're going to use our calculator. You can use any calculator that you want for your notes, but I believe that your test is going to be scientific. So we're going to enter in e to the negative second power. So in my calculator, I'm going to put in my e, so that's going to be second ln. And so you're going to see an e raised to, and I'm going to raise it to the negative second power. And I'm going to close my parentheses, and when I do that, I end up getting the answer of 0.135. We always want to round our answer. So 0.1, so what we're going to see on the display is 13533522832. But what I want you to do is I want you to round to the nearest thousandth to make that 0.135. So we're going to round to the nearest thousandth. And what we did is we entered in second ln on our calculator and then entered in -2 and then pressed enter. That's how we came up with our answer. Let's go ahead and look at example number 3. We're going to use a calculator to evaluate the expression. So in my calculator, I'm going to press second ln. That's going to give me my e value. I'm going to raise it to the -4th power. Close my parentheses and press enter. And I want to round this to the nearest thousandth. And my nearest thousandth is going to be at 0.018. So this is approximately 0.018. And finally, we have e to the 0.36 power. So I'm going to press second ln, raising it to the 0.36 power. I'm going to press enter, and I end up getting 1.433, rounding it to the nearest thousandth. So this is approximately 1.433. And that is it. That's all you'll have to do when it comes to evaluating a natural base expression using a calculator. So now what we're going to do is transition a little bit to graphing these types of functions. So graphing natural base functions is exactly the same, for the most part, as graphing an exponential growth function. So we have y is equal to a times e to the r times x minus h plus k power. This r value is a new concept. The r indicates a horizontal shift. It could be not a shift, a horizontal reflection, or like a reflection across the I think the best way I'm going to call it is we're going to call it a reflection across the y-axis. That makes more sense. If r was a number other than -1, then it would be a horizontal stretch or compression, or a horizontal stretch and shrink. But we're not going to talk about that concept in this class. You'll talk about that concept more in pre-calc and in calculus. So for right now, we're going to work with r being a reflection across the y-axis instead of it being a reflection across the x-axis. Everything else that we have already learned when it comes to exponential functions is going to be the exact same. Please note that if a is greater than 0 and r is greater than 0, then that means the function is an exponential growth function. So what that means is that your a value is going to be positive and your r value is going to be positive as well. This is going to be exponential growth for y is equal to e to the x, because technically this is y equals 2.718 to the x power. And 2.718 is a base that is larger than 1, which indicates that this is exponential growth. The only time when it's going to be exponential decay is where your a value is positive, but your r value is negative. So if you see a negative r value, that indicates that you're going to have a reflection across the y-axis, and you now will have an exponential decay function. So that kind of is related to what I talked about in the 7-2 lesson, about when we have growth and when we have decay. So please note that the parent function ordered pairs are still going to be 0, 1, and 1b, but your parent function ordered pairs of 1e since E is your B value, you're going to use the ordered pairs 0, 1, and 1, 2.718. You're going to approximate, whenever you plot these points, you're going to approximate where it's located on the graph. So we're just going to be working with very small decimals, but we're going to be working with decimals a lot. Please note that, that this is going to be reflected over x is equal to 0. So it'll be reflected over x is equal to 0, which x is equal to 0 happens whenever we have ourselves an exponential decay function. So that's what x is equal to 0 is a vertical line, and that'll happen whenever your r is equal to 0. So that's where this belongs. All right, so now let's go ahead and make sure that we're ready to go for our graphs. The thing that I want you to write down is the things that you'll see, things that we already know about graphing these functions. The first thing is our a value. If our a value is negative, that means that we're going to multiply all y values by -1, and we have ourselves a reflection across the x-axis. But if your r value is negative, that means that your x values will be multiplied by -1, and that's because r is located next door to where x is. So it's located next to x. So that means that x would be multiplied by -1 in the reflection column. And this indicates a reflection across the y-axis. Your h value is going to be the exact same as what we've done in the past. It's going to be the opposite of what you see. And that's going to be in your translation column. And we're also going to have our k, which k is exactly what you see. And that's also going to be in your translation column. Also, when it comes to your a value, if the absolute value of a is greater than, is not equal to 1, should I say, if it's not equal to 1, we're going to multiply all y values by the absolute value of a, and that's going to be located in our stretch column, our stretch shrink column. So the only thing that's going to be different is our r value being negative. So let's go ahead and graph these functions before we think about it way too much and then we overthink it. So let's go ahead and look at letter A. For letter A, we want to graph each function and state the domain, range, and asymptote. Your asymptote is still going to be based on your k value. It's still going to be y is equal to k, and it's still going to be a horizontal line. So I'm going to create a table. Just like we did before, we only need 2 points in order to graph these functions. My parent function is going to be 0, 1, and 1, 2.718. So my a value in this case is equal to 2. My b value is equal to e, which is 2.718. My h value is equal to 0, and my k value is equal to 0. So I have my parent function. In this case, we don't have a reflection, and that's because my a value is not negative. We will have a stretch, so that means I'm going to multiply all values of y by 2. So I'm going to have 0, 2, and then 1, comma, and when you multiply 2.718 times 2, you'll end up with 5.44. If you want to write it simply as 5.4, that's fine as well. Because it's just going to be an approximation of where we graph it. Now we have our translation, and in this case we have none. But before we actually graph this function, which the last ordered pairs, these are the ones that we're going to plot. But before we do that, I would recommend that you identify your domain, your range, and your asymptote. Our domain will be all real numbers, just like we've always had. Our range, in this case, because we do not have a reflection across the x-axis, we're going to have a y is greater than, and it's going to be y is greater than our k value. So that's going to be y is greater than 0. And my asymptote is going to be y equals 0. So we always graph our asymptotes. Even if it means that you need to get a highlighter out so that you can actually see your asymptote, we always graph that first. Then I'm going to plot 0, 2, and 1, 5.44. And I'm going to draw a smooth curve going through these points, approaching my asymptote, making sure it does not cross. And I'm going to make sure I have an arrow pointing up. So we want to make sure that you have an arrow pointing on all sides. Let's go ahead and look at letter B. For letter B, we have an A value that's equal to 1 since there's not a number that we can see right in front of the E value. We have an R value this time because we have this negative that's in front of the parentheses, so R is equal to -1. We have an H value that's the opposite of what we see, so the opposite of a +1 is a -1. And we have a K value that's exactly what we see, so that's going to be -2. So I'm going to write parent function first, and that's going to be 0, 1, and 1, 2.718. For our reflection column, in this case, we do have a reflection, and that comes from our R value. So that means all of my X values are going to be multiplied by -1. If my A value was -2, then a negative number as well, then that would mean that our Y values would also be multiplied by -1. But in this case, we have just a reflection across the y-axis, so I'm going to multiply all x values by -1. So I have 0, 1, and -1, 2.718. Now, next, we have stretch shrink, and in this case, my A value, the absolute value of A, equals 1. So that means that because it does equal 1, we're not going to have a stretch in this column. Next, we have translation. So I'm going to take my previous values, and I'm going to take all my X values and subtract 1, and all my Y values, and I'm going to subtract 2. So I have 0 minus 1, which is -1, and 1 minus 2, which is -1. So -1, -1. And -1 minus 1 is -2. And 2.718 minus 2, that's equal to 0.718. These are the ordered pairs that we're going to plot, but before I do that, what I'm going to do is I'm going to identify what my domain is going to be, my range, and my asymptote. Now, my domain in this case is going to be all real numbers, and my range, because we just have a reflection across the y-axis, that means that my range is still going to be y is greater than my k value, and my k value is -2. If you see a reflection across the x-axis, that means that your A value was negative. That's when we would have a less than symbol for your range. If you're confused about what your range is going to be, graph the function first, then determine what your range is. My asymptote is going to be y is equal to k, so that's going to be y equals -2. So I'm going to plot y is equal to -2. Notice that our scale is going by 2s. So you can make it go by 2s or you can make it go by 1s. I think based on the numbers that we have here, let's just make them go by 1s instead of going by 2s. It's not going to hurt anything. So I'm going to plot y is equal to -2. So I'm going to make that down here at the very, very bottom of our scale. And I'm going to plot -1, -1, and then -2.78. So that's going to be almost at 1 up here. So my graph is going to be approaching my horizontal asymptote, and it's going to be a decreasing function. And the reason why it's a decreasing function is because of the fact that my R value is negative. Notice that our graph is above, it's pointing up, so that's why our range is going to be all values of y above or greater than -2. Our last example, I'm going to create my table just to get it ready to go. And I have my A value is equal to 2, my R value is equal to -1, my H value is equal to 0, and my K value is equal to 3. If you want to put a +0 up there in the exponent position, that's fine, but you don't have to, just to establish that your H value is 0. So now I'm going to identify what my parent function is, so that's going to be 0, 1, and 1, 2.718. We have a reflection. My A value is positive, so that means I will not be multiplying my Y values by -1. However, because my R value is -1, what that means is that all of my X values will be multiplied by -1. So I'm going to have 0, 1, and -1, 2.718. Then we have stretch shrink. And in my stretch shrink column, I'm going to multiply all Y values by 2. So we go back to normal. My A value is a number other than the number 1. So all Y values will be multiplied by 2. So I'm going to have 0, 2, and -1, 5.44. And then translation. All of my X values will remain the same. So we have X plus 0. And then Y is going to be increased by 3. So we have Y plus 3. So I'm going to plot the point 0, 5, and -1, 8.44. All right. Before I plot these points, what I would recommend that we do is that we identify our domain, our range, and our asymptote. And like I said before, if you don't want to identify your range until you're finished graphing, that's perfectly fine. My domain is going to be all real numbers, and my asymptote is going to be Y equals 3. And then my R value, my range, should I say, is going to be Y is greater than my K value. It's going to be Y is greater than 3 because of the fact that we just have a reflection across the Y axis, not a reflection across the X axis. If we had a reflection across the x-axis, meaning our A value was negative, then we would have a less than symbol for our range. But like I said, if you want to wait to identify your range at the very end, that's perfectly fine with me. I'm going to come on up and plot my asymptote first, just to let me know where my goal is, where I want to have my curve kind of approach. And I'm going to plot 0, 5. And it looks like I can't plot -1, 8.44. So -1, 8.44 is somewhere up here. But I do know that my function's going to approach it. So I'm just going to have my arrow pointing up. And then my graph is going to decrease and approach my asymptote. Always make sure that you have a little bit of space in between your graph and your asymptote. That's always important. You never want your graph to touch the asymptote. And please know that it's okay just to plot one point, especially if you know what the shape is supposed to look like. That's okay. All right, let's go ahead and move on to our last example, and our last couple of examples, and that's applying our E function. So this example number 5 is going to be very quick, and 6 and 7 will be probably just as quick. So it says the, not then, the number of camera phones shipped globally can be modeled by the function y is equal to 1.28 e to the 1.31 x power. And that is where x is the number of years since 1997, and y is the number of camera phones shipped in millions. So we want to figure out how many camera phones were shipped in 2002. So what we need to do is we need to figure out what our x value is going to be. If x is supposed to be the number of years since 1997, we need to figure out how many years is 2002 away from 1997. So my t value, or my x value, should I say, my time, is going to be equal to 2002 minus 1997. And 2002 minus 1997, that's equal to 5 years. So we're going to let x equal 5. So I'm going to write y is equal to 1.28 e to the 1.31 times 5 power. What's cool about this problem is that E is not a variable, it's a number. So we can put that into our calculator exactly as we see it. So in my calculator, I'm going to enter in 1.28 times E, and it's going to be raised to the 1.31 times 5 power. So I'm going to close the parentheses just to establish that that's the ending of my power. And I'm going to press enter, and I end up with 895.03. So I'm going to write this as 895.03. Well, you can't have 895.03 graphing calculators because that just doesn't make a lot of sense. So what does that mean? Well, that's going to be 895.03. You can write that as million camera phones. That's fine. Or you can multiply this by a million. I think I have enough zeros. I believe that looks like a million. And I'm going to press enter. And we end up getting 895032542, or 43 if we were to round it up, million camera phones. Or I'm sorry, camera phones, because we already have it in millions. Camera phones. And that's it. What's cool about these types of problems is that you can just put the whole thing into your calculator to come up with an answer. If you wrote your final answer as 895.03 camera phones, or million camera phones, that would be fine too. I can accept both answers. Because the whole point is, can you come up with the answer by entering the information into your calculator? That's what essentially I'm assessing. All right, so now our very last formula, how we can apply E functions to interest rate. So this is called continuously compounded interest. So that's interest that it is being compounded over and over and over and over and over again by a computer. It says when interest is compounded continuously, the amount in an account after T years, so the amount in an account after T years is given by A equals P times E to the RT power. This is a formula that you have to memorize, and we call this the PERT formula. And we use the PERT formula whenever you see the very, very important and special word called continuously. If you do not see the word continuously, you do not get to use the PERT formula. You'll have to come up with something else. So once again, your A value represents the final amount in your account. It's the final amount after a certain period of time. P represents your principal amount or your starting amount. And R represents your annual rate. And we always represent that rate as a decimal. So let's go ahead and look at number 6. It says you deposit $3,500 in an account. So that's going to be your principal in an account that pays 4% annual interest. So that's going to be your rate. That annual interest is compounded continuously. This tells you you have to use the PERT formula. What is the balance after 1 year? So after 1 year, that means that our T is going to equal 1. So we want to figure out what is the balance. That's your A value. That's what we want to find. So I'm going to say that A is equal to 3,500 times the letter E raised to the R power, so R is going to equal 0.04 times T, so that's going to be times 1. And we put that into our calculator exactly as we see it because technically that's the whole thing is a number. So there's nothing for you to really simplify. So I'm going to write 3,500 times E to the 0.04 times 1 power. And your answer is going to be $3,642.83 or 83 cents. We want to make our answer look like money. I think it's 84, excuse me, 84. If I look at my calculator, it was 0.837, so I need to round up to 0.84. And we always make our answer look like money, putting our dollar sign in front. Let's do that again. So it says you deposit $4,800 in an account that pays 6.5% annual interest that's compounded continuously. What is the balance after 3 years? So our principal in this case is going to be $4,800. That's how much we're initially investing. Our rate, we're going to write that as a decimal, 0.065. It's compounded continuously, which means I'm going to use the PERT formula. We want to find what our balance is going to be, and this is taking place over 3 years. So A equals my principal, which is 4,800 times E to the RT power, so 0.065 times 3 power. And I would put that into your calculator exactly as you see it. So we have 4,800 times E raised to the 0.065 times 3 power, and that's equal to, our amount's going to be equal to 5,830, I'm sorry, write that like a normal person, $5,833.49. And that is our answer. So that was our fourth formula. There are a total of 4 formulas that you will need to know. The first formula deals with exponential growth. And this problem does not deal with interest. And that is simply y is equal to a times 1 plus r to the t power. Then we had our second formula that deals with exponential decay, which is the exact same formula. Y is equal to a times 1, but because it's decay, we're going to write as 1 minus r to the t power. Then we had 2 interest formulas. The first interest formula is for interest that is not continuous. And that formula is A equals P times 1 plus R divided by N raised to the NT power. And N represents the number of times that interest is being compounded. And our fourth formula is another interest formula, but this is where interest is compounded continuously. And that formula is A is equal to P times E raised to the RT power, and that is PERT. These are your formulas that you will need to make sure that you know and study. Please make sure that you know them. You can use them. You can tell which ones that you use during whichever scenario. It's going to be incredibly important for you to keep track of all of your formulas. That is the end of this lesson. If you have any questions over anything, please feel free to email me. Otherwise, I hope you have a wonderful day.